exactly what that is in a bit. Okay, the quadratic function shown at the right. So you see there's a graph in your notes at the right. It is the graph for x squared plus 2x plus 4. Okay, I did this on I actually did that on a graphing calculator on the computer and then cut and pasted it. Okay, it does not intersect the x-axis. Therefore, there are no real solutions to this problem, only imaginary. So the first thing that we're going to deal with is pure imaginary numbers. An imaginary unit is defined as I squared equals -1. The number I is the principal or main square root of -1. Normally, we never square root a negative number. We always say no real answers, right? No real solutions, right? But in the imaginary world, we get to do that. So I itself is equal to the square root of -1. Okay, so you have a chart there, but I'm also going to put this chart up here so we can refer to it. Okay, so I is the square root of -1. I squared, it equals -1. I cubed equals -I, and I to the 4th equals 1. Okay. We'll get to this part in a bit. Okay, this is I to the 1st, basically. It's tossing now. Okay, moving on. Numbers in the form of 6i, -2i, and I square roots of 3. These are called pure imaginary numbers. They are square roots of negative numbers, negative real numbers. Okay, so in example number 1, we're going to deal with just pure imaginaries. Okay, I have the square root of -25. Well, that means that I have the square root of -1 times the square root of 25. So square root of -1 is what? It's just I times the square root of 25 is 5. So our answer is 5i. I also will just tell you in future, we will always put plus minus in front of this 5i. Okay, because truly both the square roots are a positive and a negative. Okay, the next one, we have the square root of -144. Again, square root of -1 times the square root of 144. So I have I times 12, which is a 12i. Notice how we always put the number that the imaginary unit is attached to. We always put the number in front of it. Okay, so what does it look like when you're just looking at it? What does that look like? It looks like a variable, right? So treat it that way. It is treated that way. Okay, it isn't a variable, but it's treated like a variable. It's its own unique thing. So we have to treat it as if it's its own unique thing. Okay, square root of -27. This is not a number that we can strictly square root, right? So this is the square root of -1 times, is there a square that is a factor of 27? Do we have a square that is a factor of 27? Remembering that our squares are what? 9. 1, 4, 9, 16, 25, 36, etc., etc., etc. 9. And then times the square root of 3. Because what's important is if we have a number that is not a square, we simplify that square root. Okay, if we have a number under our square root symbol that's not a square, we have to simplify. So here we have I times 3 times the square root of 3. Again, the 3 comes in front of the I times the square root of 3. Okay, what about
Measurement.
okay, look at the next one, negative 216. Is there a square that is a factor of of 216? And if you're not sure, could you test and see? Could you try some of these different ones? It's 49, 67, then 64, then 81, then 100. By the way, if you know these, whew, it will make your life so much easier going forward. Sorry?
Is there any after 100?
Oh, sure. 121, 144, 169. So 11, 12, 13, 14 is 196. Yeah. And then 15 is 225.
Yeah.
Yeah.
196.
Yeah. If you know those, it will really help you going forward because we're going to do lots and lots of things with squares and square rooting. So did we find something yet?
36.
Yes. Square, is that what you're going to say, Ally? Times the square root of, it'll be 6. Okay, so we have I times 6 times the square root of 6, so 6I square roots of 6. Not bad. I think it's kind of fun. Because there's never been a time in your math life up to this point where you've been able to do a square root of a negative number. You've always said, oh, that's no real solutions. But indeed there is. It just goes into this complex idea. Okay, powers of I. Divide the power of I by 4 to determine its value if the answer ends in. Okay, so over here, we already wrote these down. We have I to the first, I to the second, I to the third, I to the fourth. The first one, I to the first is just I, right? In a sense, because it's square root of -1. I squared, when you multiply 2 i's together, you get a real number, -1. If you do 3 of them, you get a negative I. If you do 4 of them, you get a 1. Okay, then it repeats. I to the 5th is I. I to the 6th is -1. I to the 7th is I. I to the 8th is 1. And it repeats. I to the 9th is I. So you see, you have a chart there on your notes that gives you all of those iterations. So you have 4 different iterations of this imaginary unit. Okay, so if you divide that number, that power number by 4, and it ends in 0.25, that will give you the I itself. Okay, if you do a division by 4 and you get a 0.5 as an answer, that will give you the -1. If you do the division and you get a 0.75, that will give you a negative I. If you get a 0.0, that will give you a +1. All right, so for example, if I had I to the 20th, 20 divided by 4, what's that going to give me? 5.0. So I to the 20th is equal to 1. Okay, I to the 35th. Okay, if I take 35 and I divide it by 4, what number do I get? Your calculators.
8.25.
No,
8.75.
8.75. 8.75. Therefore, I have I to the 35 is equal to -I. Make sense?
No.
Okay, if I had, oh, let me think, I have to think about. Let's do
How is it?
I to the 27th, okay? 22 divided by 4 is what number?
5.5.
5.5.
Should be
See,
equal.
it ends in 0.5. Therefore, I to the 22 is equal to -1.
Ah, okay. So it has to end.
You just look at these. I find that these were the easiest way for students to remember. So that's why I chose to do it this
Yeah.
way. Because the other way you can do is remainder of 1, remainder of 2, remainder of 3, right on.
Ugh.
For some reason, that was harder for people to remember because
Yeah.
you haven't done remainders since you were in grade school.
Yeah, that's been a long time. So I hate one.
The decimal seems to make more sense to me.
It's weird.
All right.
With the long.
Oh, that's all right. We're coming to another one of those kind of problems. Okay, so example 2A, we have -5i times 3i. So what do you suppose we're going to do here? Emma, what do you think we're going to do? Are we going to do our multiplication in any different way than we normally do multiplication? No, we're not. So what would you give as an answer, just looking at that, if the i's were variables? What would you say is the answer to this multiplication? It's an I times I, which is,
Oh, I swear.
okay. But an I squared is what? Oh, an I squared is -1, so -15 times -1, we actually have 15.
Oh, my brain.
Okay, so just multiply the normal way. You multiply number to number and i's to i's, but then you have to stop and think, if I get an I squared, that actually causes a real number -1. Okay, so you'll have to fix that and make sure that you get a real number answer. Okay, the next one. -6 square root, and square root of -6 and the square root of -15. Okay, here's where it gets a little tricky. Because I know you're going to feel like, well, can't I just multiply that -6 times that -15 and get a positive answer? No, I'm so sorry, you cannot. You cannot do that. This breaks into square root of -1 times the square root of, how about if we make this into its factors, its prime factors? What would those be? 2 and 3. So 2 times 3. There's a reason I'm doing this. Okay?
This is why you learn factoring when you're like.
Yes, that's why you want to learn how to factor really well, because boy, oh boy, do we ever use it. And this would be a 3 times 5, right? Okay? Everybody have that? Okay, what is this? That's an I, and what's this? Also an I, and this is all multiplication in between all these things, okay? So this is actually I times I, which is what? I squared. Don't do anything with it yet. Okay, now I want to look at what's left here. The square root of 2 times 3 and the square root of 3 times 5. So it's the square root of 2 times 3 times 3 times 5. Do I have a square in there? Yes, I have a square. I see it right here. That means that 3 can come out from underneath the square root symbol. So basically, I have a -1 times, what is the square root of 9? It's just 3. I'm going to put a 3 there. And then it leaves me with the square root of 2 times 5, which is 10. So my answer is -3 times the square root of 10.
I feel like this just defies everything your brain wants to think about math. You're like, no, that's not how it's supposed to work. That's why we have things like 11 to 12. 11 to 11. What? 11 to 11. Oh.
The thing that what I kind of love about it is, if you are willing to put the detail down, it's actually pretty easy math to do. It just requires you know, paying attention to what's actually happening. Okay? In point number 3, where we're solving quadratics with imaginary solutions, sometimes we can use this square root property. Okay, the square root property says that x is equal to the square root of x squared, right? Or x squared is equal to. Is that right? I think that's right. If it's not, I'm sorry, but we know that if you square root x squared, you do get x. Okay. Go with that idea. Okay, we have 4x squared plus 256 equals 0. Right? So if I turn this into this kind of an equation, I'm going to put 4x squared on this side equals negative 256. Right? Once I have a square on this side and I have a square on this side, right, I can use the square root property, but hold on. Could I divide by 4, and make it a little simpler? Yes, you can, and please do. If there is a greatest common factor, in fact, you could have even done it on this step. It doesn't matter, okay? So I have x squared is equal to what?
Like 60/44.
All right? So take the square root, And so x is equal to plus or minus, right? We're gonna give the, not just the principal square root, but also both square roots of what? The square root of -1 times the square root of 64. Yeah, what about the 8? So x is equal to plus or minus what? No, 8. 8 goes first,
8.
and then the I. Okay, so the 64 and the I. I think one thing I left out on here was the plus minus part. Since I don't have it written in my notes, just pulling it out of my memory banks. Sometimes they get a little scrambled. Okay, moving on. To complex numbers. Okay, other operations with complex numbers. A complex number combines a real component with an imaginary component. That's what makes it complex. Okay, for example, 2 plus 3i or 16 minus 4i. The 2 and the 16 are the real components, and the 3i and the -4i, those are the imaginary components of each complex number. So to define, a complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. Okay, a plus bi, or it could say a minus bi. It's a real component with an imaginary component. Okay, now get ready for the next sentence because it will not feel like it will feel like it doesn't make any sense at all until we actually start doing it. And then I promise you it will make sense. Okay, so when combining complex numbers, we use this concept. A plus bi is equal to c plus di if a is equal to c and b is equal to d. Okay, so the a has to be the same as c, the b has to be the same as d. Or has to be equal to.
Do the I's have to be the same?
Well, the I is the same, sure.
Why are we changing the letters? To C and D?
let me explain with an example once we get to the example, okay? It will make more sense, okay? So real parts must be equal to the corresponding real number. And imaginary parts must be equal to the imaginary part on the other side. So the real has to equal the real on the other side, the imaginary has to equal the imaginary on the other side. Okay? Example. Says find x and y. You have 3x minus 5 in parentheses plus in parentheses y minus 3i is equal to 7 plus 6i. All right, so this is a real part, right? You see anything imaginary attached to that? Nope. Okay, well, on the other side of the equal sign, what's the real part? 7. Okay, on this side, you have a y minus 3 attached to an I. What do you have over here attached to an I? So you simply make your 3x minus 5 equal to your 7. And you make your y minus 3 equal to your 6. So you add 5, 3x is 12, x is 4, and add 3, y is 9. Done. I told you, once you kind of understand it, it's not as complicated as it looks. Sounds scary, but it works pretty simply.
You don't use the I outside of the, you just get rid of the I's.
You're finding x and finding y.
Oh, so we just get rid of.
So you don't have to, you don't get rid of them. You just don't need them in your calculation. Okay, they don't go away. It's just simply saying that 12 minus 5 plus 9 minus 3i is equal to 7 plus 6i. Yeah.
You can add them back in later whenever you're actually plugging the variables to make sure the equation.
That's right. If you're checking, you can plug the i's back, or you can leave.
What if
Leave
you
the
get
I.
something like this and it tells us to solve?
Well, you did just solve, huh?
But it says to find x and y, what if you have to solve like a number? Cause it's your.
You did find a number for x and y. You did solve. We did solve.
So we don't, but what if you came to a point where you had to plug them back in and then find, and then use the I and.
We also talked through that. We
You?
did. We talked about it.
Oh.
We said if you take 12 minus 5, what do you get? 7. If you plug it back in. We did just that. We did it
Oh, yeah.
verbally. We did it verbally.
Okay.
Okay, so moving on down, when adding and subtracting complex numbers, combine only like terms. When multiplying, use FOIL. Okay, so A says 5 minus 7i plus 2 plus 4i. Okay, what are we going to add together? 5 and the 2, that's a 7. Negative 7 and a 4.
5 and 2 would be 10.
We add Always make sure you look at the symbol.
Oops.
If there's a
Foil
symbol
with the I and
between,
2.
if there's a symbol between, you have to use it.
What? Why are you?
Real with real, that's 7.
What?
Imaginary with imaginary, that's -3. It's not what?
Multiply.
Yeah, don't multiply when there's a plus sign in between.
I
Okay,
didn't know you could do foil with plus signs too.
it's not a FOIL. This is not FOIL, this is addition. Okay,
Oh, it says no.
this is an addition problem.
So we don't-
Okay. B says 4 minus 8i minus 3 minus 6i.
So.
Okay, please. Okay, just a second, please. If these kind of problems are an issue for you, if they trip you up, please turn them all into addition problems. This is subtraction, but you can very easily turn it into an addition
by making this a plus sign and then changing the signs of the numbers that are inside the parentheses. Because that becomes a -3, that becomes a +6i.
Okay, because these problems, of all the problems I do, these tend to trip me up. So I always turn them into additions.
So that I can immediately see I have a 4 -3, that's a 1. And a -8 + 6, that's a -2i.
A lot simpler than I was thinking.
Mhm. Okay, which then leads us to our multiplication one. Do we have this? Everybody got it written down? If you did, do you have it done? Okay. Okay, the multiplication ones will not have a symbol in between, right? They will just be two binomial factors. 3 - 2i times 5 + 7i. I will use FOIL, not the box, but you can use the box if you want, okay? So FOIL is first terms first. 3 times 5 is how much?
15.
Okay, 3 times 7i is
Plus 20.
+21i. -2i times 5 is
-10.
-10i. And -2i times 7i is
-14i squared.
-14i squared. All right? So basically, we have a 15 plus, what is the 21 and the -10?
11.
11i, and then what? What is this?
14.
+14. Why?
Oh,
Because it's -14 times -1, so it becomes +14. So I have 14, I add it to my 15, I get 29 plus 11i.
Why? did-
Yes, you have to be really careful. You have to be really careful that you capture these I squareds as -1s,
Wait,
okay?
why didn't you add them too?
What do you mean?
Why didn't you add the 3 and the 5 and -2i and the 7?
There's no symbol in between.
Okay.
When there's no symbol in between, it's a multiplication. Yeah, it would have to have a plus or a minus sign to do that. Okay, last concept. This is probably the trickiest one.
Wait, we're dividing.
Okay, so when dividing a complex number, you cannot have a complex number in the denominator. You need a conjugate. So a plus bi and a minus bi are conjugates. Multiplying them together yields a real number. Right? So example, 2i over 3 plus 6i. Right? I want the conjugate of this so I can get rid of that complex number in the denominator. So I'm going to put a 3 minus 6i over a 3 minus 6i.
Wait, what?
Why?
Oh, just the denominator.
Because what is this expression? What is a phrase or an expression or a number over itself? Listen,
1.
what is this number? This number is 1. Just trust me. I will show you exactly why. Okay? I'll show you exactly why. Okay? Because 2i times 3 is what? 6i. And 2i times -6i is what?
-12.
-12i squared. We'll fix it in a minute. Okay? All right. What is 3 times 3?
9.
9. But look, what is 6 times 6?
There's negative.
36i squared.
And what do I need in between them?
Just a minus sign.
Why do I need just a minus sign? Because I have a 3 plus 6 and a 3 minus 6. Right? 3 plus 6i, 3 minus 6i, square the 3, square the 6, and put a minus sign in between them. Okay? So up on top, I have 6i
Plus.
plus 12. On the bottom, I have 9 minus 36 times -1. So I have a negative, that's 36 times -1, which is plus 36. So therefore, I have 6i plus 12 over 45. Be careful. 3 goes into this. 3 goes into this. 3 goes into this. You must also simplify. So 2i plus 4 divided by 15.
How do we show
That
that we
is
did
your-
that for free, or can we just equal it to something?
Sorry?
Do you want us to show you that we divided it by 3? Or can we just do what you did on the board? And
You can just do what I did on the board. Just simplify. Deeper. That is the end of our session. You guys feel good? You feel like it wasn't quite as bad as you thought it was gonna be?
A little bit.
It still just makes me.
It's very fun, right?
Yeah.
This isn't